Hello friends and hello respected sir. I'm Pranali Vaydande from ETRXA and I'm here to present a paper review on the topic an Internet of Things enabled smart system for wastewater monitoring. So these are the authors of the paper and date of publication is 5 January 2022 and publisher is IEEE. So this is the abstract of the topic. So we represent and evaluate an IoT enabled sensing and actuating system for localizing illegal industrial harsh discharge of polluting waste water in sewer networks. The special condition of the sewer environment brings the special challenges for the design of an IoT system and its real-time algorithm for anomaly detection and localization of the wastewater networks. So here we are going to see an architecture which is used for the detection of industrial harsh discharge of polluting wastewater. So the architecture is known as HADA. HADA means hop by hop, anomaly detection and actuation system. So in introduction, we are going to see a new hardware architecture for wastewater monitoring IoT system, a distributed real-time algorithm for anomaly detection and localization of harmful wastewater and discharge of constant IoT devices. Next is a new IoT architecture pattern that can be reused in other applications and environment with similar constraint. We are going to see results with verification and validation and simulation of the same. So now this is the hardware architecture of the HADA. So this is how it looks. It is actually located or it is situated in a place where the industries are placed. So the first topic in this architecture is localization of polluting sources in sewer main line. So the first is this. So the main operation principle used by Micromole for localization of polluting sources in wastewater are first two IoT devices. So the first IoT is pH and second is EC sensors. So the two both are very important sensors which are used in the architecture. These IoT device are one is used before the private inlet and another used after the private inlet, which is the first one is used the pH and the second one is used the EC. The pH is used for acidity and basicity, that is to know the pH value or the level of the water, and EC is used for to know the purity or purity which is purity of the water. Next is the remote installation and the extraction of micromole IoT devices in sewer pipes. So the wastewater network is composed of sewer pipes different diameters. The diameters of the target pipes for the micromole system affects the dimension of the sensors. So we selected DN250 as the minimum acceptable pipe diameter for the IoT device after an analysis for the sewage pipe diameter. So this has been used in every HADA architecture. The DN250 diameter is used for every HADA architecture because no other pipes can be used because the normal sewer pipes are 120 mm diameter, which can spoil both the sensor devices. So next is, so this is how it works. This is the crawler robot installation inside a sewer pipe. So this is two DN250 pipe in which this crawler has been installed. So next, distributed anomaly localization algorithm of harmful water discharge. So these are the topic we are going to discuss under it, that is distributed IoT based processing and anomaly detection algorithm. So the first, this is the software architecture, that is the hosting the anomaly localization algorithm of on the IoT device implies the careful design of scalable resources constraint algorithm that work in real time. Presents the software architecture used for such functionality distribution. Each of the IoT devices have implemented a sensor driver module that periodically queries the measurement attached pH and EC sensor for measurement through the drive through the device bus. Each measurement is collected by the anomaly detection algorithm within each IoT device for detection of abnormal suspicious pattern in the last sequence of measurement. Next is anomaly detection algorithm. So anomaly detection algorithm is only possible if contextual information is properly defined. Defining a normal context in a complex for wastewater sewage network, it shall be considered that pH level and EC measurement are seasonal. The level pH and conductivity are aggregated wastewater in the sewage network changes slowly during the day in the normal conditions. As it can be observed that the pH level and EC fluctuation continuously during the day and in the sewage system. During the night by the user of the sewage system, during the night there is usually no wastewater flow, both physical characteristics drop, that is EC and pH level. You can see in a time, that is 15, 18, 21, 0 and 3 again. So every time you can see till 12 it was high and after 12 it comes down. So according to it, in the night the wastewater flow are less. Next is simulation results. So as you can see the graph which shows the simulation results. Simulation results. Discharge simulation system. We simulated the dilution behavior of the sewage network system. So here, when the industrial waste substances is discharged from each building separately, a simulated event consists on the discharge of either 50L or 100L of a substance from in a selected building in at either low or high wastewater flow in a flow conditions. Therefore, there are 104 different simulation scenarios where when the considering all 42 buildings or two flow conditions or three substances or two different discharges volumes. So from each simulated event we obtained a set of time series of EC and pH measurement as observed through the transversing manholes in the network. An experiment is defined as a time series measurement of EC and pH at a single manhole from a simulation. Since there are 285 combinations of building and manholes due to flow directions of the wastewater network, and total number of experiments was 3,420. So this is how they do the installation of IoT assembling of for testing. So the right side one is the EC module and the left one side is the pH module. Yeah, for detection in every building they use. Next is the system verification in a real sewage environment. So here we are going to see the system configuration, hydraulic conditions, substances used for system verification and result analysis. So the first is system configuration. Okay, in a test bed at KVB consists of gravity sewer with a nominal diameter of 350 mm and a length of 222 m. The sewer is fed with wastewater from a pumping station through a chopper pump. The wastewater is a mixture of industrial and domestic wastewater drained in a combination of separate and combined sewers. A regular check of wastewater composition confirmed that no significant amount of rainwater or a groundwater had penetrated the connected sewer during the test. Next is the hydraulic conditions. During the test, the water level or the flow rate and the velocity could be adjusted in order to simulate hydraulic conditions that are typical for municipal sewer system by adjusting flow rate and velocity, dilution of discharge substance and flow time between our IoT devices could be varied by lease. Flow rate and velocity of the sewage were adjusted by the regulating and frequency of pump according to the values given in IoT systems. Next is substances used for system verification. So the substances used for our experiment were chosen so that the pH and electric conductivity could be influenced independently in one another. Therefore, any combination of rising falling pH could be achieved with or without a simultaneous increase in conductivity as well as an increase in electric conductivity without a significant change in pH. So next is results analysis. So the pH and EC baselines of the pH and EC baselines of an EC references and master devices for discharge. So number 8 of can be the number 8 name. Sorry. The pH, EC and baseline of the reference and the master device for discharge can be observed. In this case, both devices detect the anomaly since the discharge was made in front of the reference device with the difference of nearly 2 minutes due to the flow rate and with the different magnitude due to the dilutional effects previously explained. Since both devices detected the event, the master device did not request the sampling action from the sampling device. So the same outcome can be achieved by the discharges. So next is the conclusion. So the in a micromole IoT system, like system and the distributed anomaly detection algorithm for localization of the harmful wastewater discharges in the sewage. Here we understood like how we can measure the pH or the EC, or how we can stop from using from polluting the water in sewer network. So there are some drawbacks of this also, like the unstable internet connection is in the underground pipe, the lack of power grid energy supply in the sewage network, and the end users need for triggering the IoT device. Actuators in real time brought special requirements for the design of our anomaly detection and localization algorithm. Such requirements were fulfilled by using IoT architecture. The new IoT architecture was generalized as an IoT architecture pattern with the name hop by hop anomaly detection and actuation HADA. So it could be reused in other contexts and applications. So it is actually verified. The IoT, the proposed IoT system was verified through simulations in a large sewage networks and also implemented in in a foreign countries. It was implemented under the sewage networks. So it actually worked in other countries. May we use the same technology in India also. I hope so soon we'll use it. And this can be used actually. This is the perfect architecture or the system for detection the chemicals or the acids or anything in the water which are polluting it in a sea or a ocean. So we can see many things, like we can IoT is actually upgrading in every field. So thank you to listening, and thank you so much.